Welcome to section 10.8. Here we are going to be talking about the concepts of arc length and curvature for vectors and space curves in 3D. So we're going to start off by talking about arc length. So given a vector function r of t whose components are f, g, and h, all in terms of a parameter t going from a to b, where all of the first derivatives are continuous for these functions, if the curve is traversed exactly once as t increases from a to b, then its length can be found using the formula L equals the integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. This formula, when written in a shorthand form, this is basically the expansion of the magnitude formula, right? You take the components of the vectors squared, add them, and take the square root. This is really just the formula for the length of r prime, right? If r is fgh, then r prime is f prime, g prime, h prime. So this is just the length of r prime of t dt. So these are two equivalent formulas that both represent the same thing, that being arc length over a segment of a curve in 3 space, as it is traversed exactly once using the values of the parameter going from a to b. So let's take a look at an example. So find the length of the arc of the circular helix with this vector equation, cosine t, sine t, and t, from the point 1, 0, 0 to the point 1, 0, 2 pi. So we saw this curve in a previous section. We looked at the sketch of this curve. It was that circular helix going like that. Now we're going to find its arc length. So we need to get the length of r prime. So let's put down r prime here first. So r prime of t is going to be negative sine of ti plus cosine of tj plus 1k. So the length of that's the square root, negative sine squared, so that's sine squared t plus cosine squared t plus 1 squared. We know via trig identity that sine squared plus cosine squared is 1. So this is the square root of 1 plus 1, or just radical 2. So this is going to be our integrand, right? That's going to go in here. The only other thing we need are the bounds. All we have at the moment are these 2 points. So we need to go ahead and find the value of t that corresponds to those bounds. You can solve it using any of the components, although I think k is probably the easiest one, because if the k component is just t, and we go from 0 to 2 pi like that, that means t goes from 0 to 2 pi, right? And you can check like cosine, it goes from 1 to 1, so it makes a full rotation. Sine goes from 0 to 0, makes a full rotation. But this tells us, so note t is going from 0 to 2 pi. So L is the integral from 0 to 2 pi of radical 2 dt. Antiderivative of this is t times radical 2, evaluated from 0 to 2 pi. So we get 2 pi root 2 minus 0 root 2. So 2 pi times radical 2. So that is the length of this specific arc of the circular helix from 1, 0, 0 to 1, 0, 2 pi. Now, we've talked a little bit about parameterizations of curves, like we saw with this circular helix, right? We have cosine t, sine t, and t. Curves can be represented by more than one vector function. So, like, for example, if we took r1 of t to be t squared, and t cubed, with t going from 1 to 2, or we took r2 of u with e to the u, e to the 2u, e to the 3u, with u going from 0 to 2 pi. Regardless, this gives us the same curve with the connection being t equals e to the u. So these are both parameterizations of C. So the point here is that there is not one specific parameterization you can use for a curve. So like back in this example, this is not the only way to parameterize that circular helix. There are more than one way to do that. But there is one thing that is consistent. So, and this is an important note here. The arc length L would be the same in both cases. So that's an important thing to take into consideration, and why arc length can be so important for us. And we're going to encounter this later on in the course as well. But the concept of arc length is so useful because arc length will be the same regardless of the parameterization used on a curve. So, like it says right here, when we compute arc length, the answer is independent of the parameterization used. So it doesn't matter how you parameterize the curve, the arc length will be the same. So if you consider this arc length function, so s of t, where this is the integral of the derivative here. So we've just kind of relabeled the letters here. We're using u as a placeholder variable. T will be the ultimate variable in the end because it's in s right here. But if we take this function, this formula, this gives us the length of C between R of A and R of T. Differentiate this to get magnitude of R prime of T dt. Or excuse me, not dt anymore, just magnitude of R prime of T. So one of the things that we can do, and we'll kind of encounter this more later on, is we can parameterize a curve with respect to arc length, and that can give us one consistent parameterization, that even though you can parameterize a curve 100 different ways and have them all mean the same thing but look different, the arc length will always be the same. And so we like to use arc length when we can as a standard parameterization. It's not always so easy to parameterize curves in terms of arc length, but this is one use we have for arc length, is being able to parameterize curves in terms of it, so that we have kind of some standardization behind that process. Okay. We're going to go ahead and skip this example. We've got a couple notes here, so a bit of kind of setup for the stuff we're going to do. If a curve is smooth, so no sharp corners or cusps, then when the tangent vector turns, it does so continuously. So the tangent vector turns continuously. So it has a smooth parameter, r prime is continuous and not equal to 0, on the interval. We're about to talk about a concept that involves turning of tangent vectors. So this is just giving us a little bit of setup, saying as long as the curve itself is smooth and we have valid differentiation at all of these different points, then the tangent vector will also turn smoothly and continuously. So in other words, no surprises when we come upon these processes. Remember the unit tangent vector, we saw this in the previous section, is just the tangent vector divided by its own length. We're going to use that here as well. So we're going to talk about curvature. So the curvature of a curve C at a given point measures how quickly the curve changes direction at that point. So curvature tells us how quickly the curve changes direction at that point. So you can see I have a little diagram over here on the side. Notice the tangent vectors that I've drawn at each one of these points. We're not looking at the vectors themselves. We're looking at how much the graph is changing or turning at any given time. So notice like from here to here, these tangent vectors are pointed almost the exact same direction. There's not a lot of change, not a lot of turning happening here. But from here to here, these vectors do almost a complete 180 in direction from here to here over relatively the same amount of distance. So the value of the curvature here should be very high. So curvature is giving us a numerical value at any given point that will tell us how much the curve is turning or changing direction or curving, if you will, at that given point. So we have a couple different ways that we can find curvature using formulas. So we're going to give the setup first, and then we're going to get to the ones that we can actually do calculations with. So curvature, we're going to use, it looks kind of like a letter K, but it's kind of like a Greek letter K. So give it a little bit of a curve like that. So this is curvature is what this symbol represents. This is the magnitude dt ds. So this is the length of the derivative of the unit tangent vector with respect to arc length. Okay, so we got a lot going on here. But we're going to reparameterize this. So we get the following. So dt dt, that's the same thing as dt ds times ds dt, right? And then you kind of get that arc length removal from this process. So we get curvature was this, but we get dt dt up here and ds dt down here. So we want the derivative of the unit tangent vector with respect to t, our parameter, and we want the derivative of arc length with respect to t. And we showed on the previous page that this is ds dt, right? We saw that a page ago. So we can rewrite these in their prime notation. So this is going to be length of t prime of t over length of r prime of t. And this is one of the formulas we can use when finding curvature. So, for example, we're actually going to do a little bit of a proof here. Show that the curvature of a circle of radius a is 1 over a. All right. So the curvature problems, a lot of times they're just accumulation of piece problems. So we need to start with r of t, and we need to get all of the pieces and put them into the formula in the proper places. So the parameterization for a circle of radius a, that's going to be a cosine of t I plus a sine of t j. So we need r prime. So it's going to be negative a sine of ti plus a cosine of tj. So we need the length of that. So that's square root. So that's a squared sine squared plus a squared cosine squared. We can factor in a squared out of there. Of course, we encounter this same trig identity a lot, so that's just 1. So this is square root of a squared, or just a. Okay, so we get magnitude of r prime of t is a. And we also need the unit tangent vector. So now we have the tangent vector, and we have the length of the tangent vector. So those are the pieces we need, actually. So t of t, so this is r prime over length of r prime. So that's negative a sine of ti over a plus a cosine tj over a. So we get negative sine of ti plus cosine of tj. But we don't need t for the formula, we need t prime. So let's get t prime, take the derivative of that. That's going to be negative cosine of ti minus sine of tj. We also need the length of that. But that's going to end up, the negatives become positive when you square them. So you get cosine squared plus sine squared. So just 1. So that's the length of t prime of t. So our curvature which is length of t prime over length of r prime, that is 1 over a. So we do get 1 over a. So a constant curvature for a circle of radius a. And hopefully that makes sense, like intuitively, the idea of like a circle, because a circle is just one constant curve, right? It's never growing, it's never turning faster at some points and slower at others. It's always turning at the same rate as you go around the circle. And the curvature itself depends on the value of the radius, right? It's actually inversely related. So an interesting thing, so note, so if you have a bigger circle, you end up getting smaller curvature, and vice versa. So if the circle is, this big, going from here to here is not that big of a difference in curvature, right? The value hasn't changed that much. We're still pointed relatively the same direction. But if I draw a circle that's this tiny, and I take this distance, going from here, let me do this a little bit bigger, here to here, so that would be like this distance. We're going completely opposite directions. So the large circle has a small curvature, okay, because it's not curving as much from point to point as it goes around. But the small circle, it's curving and turning constantly. It's turning, and it's very quickly doing so. So that produces a very high curvature. Okay, and that's displayed by, again, this inverse relationship of 1 over a. So the larger the radius, the smaller the curvature. Most curves in space do not have constant curvature like circles do. Okay, we can find a formula for the curvature and then plug in specific points to get the curvature at a point. Now, there is another version of the curvature formula that we can use. It's not going to look any nicer than the one that we just had, but in practice, it can be a little bit easier to use in certain circumstances. So we're going to put this here. So another formula that we can apply for curvature is going to be the following. It's still a fraction, so leave yourself a little space here. It's the length of r prime of t cross r double prime of t over the length of r prime of t cubed. So this is an alternate version, an equivalent version of the curvature formula. Again, this one often being simpler to compute in many cases, but can be used interchangeably. So let's try another example using this version of the formula. So find the curvature of the twisted cubic. So that's the curve that has a vector function t squared, t cubed at a general point and at the point 0, 0, 0. So we need r prime, we need r double prime, we need a cross product, and a couple lengths here. So r prime is going to be 1, 2t, and 3t squared. R double prime is going to be 0, 2, and 6t. We need to get the cross product, so we'll do r prime cross r double prime. That's I, j, and k. So 1, 2t, 3t squared, 0, 2, and 6t. If we do the I component, so you take AD minus BC, we're going to get 6t squared I minus the j component, so block off that and do the 2 by 2, so minus 6tj. And then for k, block off those. The 0 helps, so it's just plus 2k. Okay, so as a vector, we get 6t squared, negative 6t, and 2 to go along with these. All right, we need a couple of lengths here. So length of r prime, we're going to need for the denominator. So that's going to be 1 plus 4t squared plus 9t to the fourth. The length of the cross product is what we need for the numerator. So we're going to get 36t to the fourth plus 36t squared plus 4. And now we have what we need for our formula. So we can go ahead and put in the two lengths. Don't forget to cube the denominator. So we're going to get square root, 36t to the fourth plus 36t squared plus 4 over, this is the square root and it's cubed. So I'll just put that to the 3 halves. So 1 plus 4t squared plus 9t to the 4th to the 3 halves, using just exponent properties there. So let's see, what did it want? The curvature of the twisted cubic at a general point and at 0, 0, 0. So this is the formula at a general point. We can use this to find the curvature for this curve at any value of t we want. Okay, so we have the general formula here. Now we want the point when the curve is at 0, 0, 0. So the question is, what value of t do we plug in? Well, if this is 0, 0, 0, the only point that works is t equals 0. So we get curvature at 0. That's going to be square root of 0 plus 0 plus 4 over 1 plus 0 plus 0 to the 3 halves. Radical 4 is 2. Radical 1 is 1. 1 cubed is 1. So we just get 2. So we have the general curvature formula on the left, and we have the curvature specifically at the point 0, 0, 0 on the right, which is 2. And if we were to calculate the curvature at a different point, we would get presumably a different value. We could do that for any point that we desired along the entirety of this twisted cubic, of this curve. All right, the last thing to look at in this section, there's a couple more vectors that we need to take a look at when it comes to kind of mapping space curves, in addition to the tangent vector. And these are the normal and binormal vectors. So a little bit of setup here to get us to these. So at a given point on a smooth space curve R of t, there are many vectors that are orthogonal to t of t. We're going to single out one of them. So, right, we have the curve. So let me just off to the side over here. We have a curve, and we have a point on that curve. We're going to have t of t pointed, right? It's the tangent vector. It's pointed in that direction that the curve is going, and it's a unit tangent vector, so it has a length of 1. There are, again, infinitely many vectors that can be orthogonal to this one. They can go all the way around and find orthogonal vectors, but we want to look at one specifically. So since we know the length of the unit tangent is 1, this means that the unit tangent and its own derivative have a dot product of 0 by a result that we've proven previously. So this is something that was mentioned in the previous class, the idea that if a vector has a constant length, then it is orthogonal to its own derivative. So the dot product is 0, thus t is orthogonal to t prime. So that's the vector that we're going to single out. So this is what we call the principal unit normal vector, abbreviated n of t, so capital N. This vector is t prime of t divided by the length of t prime of t. So it's the derivative of the unit tangent, and it's a unit vector because we divide by its own length. So this unit normal vector, this vector is orthogonal to t. It's going to be right about here. Okay. And there's an important thing to note about what this specifically is doing for our curve. So put this right here. So note n of t indicates the direction the curve is turning. So this unit normal, this t prime over its own magnitude, it is orthogonal, so they do have a right angle between them. But it specifically is pointing in the direction that the curve is headed. So t is pointed the direction the curve is currently going. N is telling us what direction we are turning along this curve. So you can see here the curve is turning to, the right, or it's turning back down this way. That's what this arrow is indicating, this vector. If we were back over here and we're kind of arcing it to the left like that, the vector would be pointed this way. Okay. So n of t does give us valuable information at any point. It can tell us the direction that we are turning at that point. And then we have the binormal vector b of t. This is going to be t crossed with n. So this one, because it's a cross product of the two vectors that went into it, we know it's perpendicular to both of them. Different color. We know it's perpendicular to both of them, so it's going to be somewhere out here. And again, it has that right angle with both of them. Okay, and the binormal vector, the thing that it gives us, so note the binormal vector gives us up versus down. So the binormal vector basically tells us what direction is up. So the way that we can use these vectors, if you think about it in the context of like air travel, think of like aerospace. If you're flying in a plane, which I'm not a good artist, but here's our plane. These three vectors each give us useful pieces of information. The unit tangent vector tells us what direction the nose is pointed, right? It tells us what direction is forward, where we're going. If you need to make a turn, the normal vector tells us what direction the plane is turning. So like if you're going to turn to the right, the normal vector is going to go to the right. If you're turning to the left, normal vector goes to the left. If the plane is going perfectly straight forward and not turning at all, then that vector is not going to appear. And the one that gets maybe the most overlooked, but is perhaps the most important, the binormal vector, tells us what direction is up. Because, of course, if you're flying a plane, you very much want to be flying with everyone's heads pointed upward towards the sky, so that gravity is holding you into your seats. But you can use these three vectors to give very specific information about where you're going. Not only the direction you're pointed, but how much you're turning left or right, and how much you are angled up or down. Okay, because if this vector all of a sudden is pointed that way, then something needs to get fixed, right? Or if your ultimate goal is to get to a point over here, we want this vector to get larger as we start turning more to head in this direction. So all three of these combined can give us valuable information, not only about where a curve is, but where it is going and how everything is oriented around it as you're moving along the space curve. Okay. So let's try an example finding these vectors. Find the unit normal and binormal vectors for the circular helix. So cosine of t, sine of t, and t. So we've got r prime of t is going to be derivative of cosine is negative sine. Derivative of sine is cosine. Derivative of t is 1. Length of r prime, we actually found this in a previous example in this section. That was radical 2. So our unit tangent vector is going to be 1 over root 2 times the negative sine, cosine, and 1. So t prime is going to be, 1 over root 2 negative cosine, negative sine, and 0. So this is the start of that normal vector n. We also need its length, which this one you do cosine squared, sine squared, so it ends up just being 1 over root 2. So our unit normal, which is t prime over length of t prime. So this is 1 over root 2 times, negative sine, wrong one, negative cosine, negative sine, and 0 over its own length, 1 over root 2. Those are gone. So we get negative cosine of t, negative sine of t, 0. So t back here tells us what direction we're pointed, so we're going around the circle. This tells us what direction we're turning. So because we're turning in a circular fashion like this vector is always going to be pointed towards the inside as we're going around the circular helix. And then the binormal, so that's t crossed with n. So that's, you can actually pull the 1 over root 2 out because they both, actually this one doesn't, but this one does. Pull that out of the middle row to make the calculation easier, because we get negative sine, cosine, and 1, negative cosine, negative sine, and 0. So again, this came from this row. So you could put it in if you don't feel comfortable with that. But do the cross product here. We end up getting 1 over rad 2, sine of t, negative cosine of t, and 1. So this gives us that upward orientation on the curve as we're traveling around it. Now, just a couple more pieces of terminology here to finish this off. So because we've created these vectors here, so up there in the purple, the orange, and the red, we actually can define planes between these vectors. So we can define the normal plane is determined by n and b, so the normal and binormal. This contains all lines perpendicular to t. So that's going to be N and B. So that's, let's see, let me do it like this. So, and it continues on in all directions here. But this plane here, this contains all lines that are orthogonal to T of T. So that plane, that is the normal plane. And then we can talk about the plane determined by T and N. This is called the osculating plane. Not oscillating like with trig functions. This is osculating. It actually comes from a Latin word, osculum, which means to kiss. This is sometimes called the kissing plane. This comes closest to containing the curve at the point P. So if we go back and look at the diagram again, so that's this plane right here and everything kind of around it there. So at the point P in question, the most we can possibly contain this curve around that point is using this plane. That's the plane that's going to contain the most of the curve possible around that point. And that's found by using T and N. And that's why, again, it's referred to as kind of the kissing plane, because it just kisses the curve at that point, right? It touches it there, and it kind of encompasses as much of it as possible before the curve starts kind of, diverging away and curving away from that point. So we can draw these vectors, the unit tangent, the unit normal, and the binormal. We can create planes between them to encompass either perpendicular lines or to encompass the curve itself surrounding that point. But that brings us to the end of section 10.8 and the end of our conversation on arc length, curvature, and these additional normal vectors when it comes to dealing with space curves.